Hi, this is Dr. Moberly, and we're going to look at kreyszig section 1.5 problem number 40. This is the section with the non-homogeneous linear ODEs, first order ordinary differential equations. This one has 20,000 cubic feet of space in a room and air exchanging at 600 cubic feet per minute and going out at 600 cubic feet per minute. And this is fresh, and this is a mixture of fresh and stale. And the idea is you put enough fresh air into there, you're eventually going to get to 100% fresh, which would be 20,000 cubic feet of freshness. That is your horizontal asymptote. Our initial condition is that y of 0 equals 0. That's starting out here. Pretty easy to see where this is going to go. This looks like upside down exponential decay. And that's at horizontal, non-zero horizontal asymptote. I think we know what that format of that would be. It's going to be some number times c to the e to the minus kt. And of course the c is 20,000 cubic feet. That's what we expect for the model. Let's go ahead and prove it. And it begins by setting up the balance equation. And that's the y prime equals the rate in minus the rate out. The rate in is 600 feet cubed. The rate out is 600 feet cubed times the concentration as a function of time. And the concentration is going to be the amount of fresh air divided by the volume of the room. The volume of the room is 20,000. So we're going to see this being equal to 600 minus 600 times y of t over 20,000. And we're going to rejuggle this around. I'm going to leave the rational expressions alone. I know that reduces to 0.03, but that particular aspect doesn't help me all that much. Let's go ahead and put it into standard form, which is the y prime plus p of x y equals r of x. This of course becomes 600 over 20,000 times y equals 600. And now we're going to do the integrating factor. Well, first of all, the h of, did it again, p of t, r of t. H of t is going to be equal to the integral of p of t dt, which is equal to 600 over 20,000 dt integrated, which is equal to 600 over 20,000 t. Now there is a plus some constant, but forget about that. Forget about it, because it will only disappear later if you were to put it in. Try that and see if you don't want to remember to forget about it. Exponentiate. So we integrate. We exponentiate. E to the ht is going to be equal to e to the 600 over 20,000. I know that's 0.03 t. Now we multiply. E to the ht times r of t is going to be 600 times e to the, oh, actually I want to write it the other direction, e to the 600 over 20,000 t 600. And now we're going to integrate, just to integrate e to the ht r of t. And this is where we need to pull something out. We're going to pull out the 20,000 so that we've got an e to the 600 over 20,000 t times 600 over 20,000. And this is why I did not choose to simplify the 0.03, because you see the 20,000 is going to be part of the problem in the end, not the 0.03. Now we've got the form e to the u du form, and of course we know that's e to the u. When we integrate it, we're now looking at 20,000 times e to the 600 over 20,000 t plus a constant, and that's the next step, is to add, and then the next step is to divide or multiply by e to the minus ht times this expression, and that's gonna, this part's gonna cancel. We're gonna just get the 20,000 times 1, and this part's going to be c e to the minus 600 over 20,000 t. Now you might ask, how do we get y of 0 equal to 0? Well, that would be 20,000 times 1 plus c times e to the 0, which of course is a 1. That tells you that c is equal to minus 20,000. That's why the constant can be pulled back out in this model. Okay, you didn't know that until you did the problem. Now we're ready to say that y of t is equal to, actually, I better use the letter A there just to differentiate it. Let's make sure that we're getting the right problem here. We've got this e to the minus ht integral e to the ht r of t dt plus a constant, and that's 20,000 minus 20,000 times e to the minus 600 over 20,000 t. We pull the 20,000 out, and now it's 1 minus e to the minus 600 over 20,000 t. And there is our model all complete. Oh, it asks a question. When does it get to the 90%? And we want to know this T90 as an answer to the problem. T90, y of T90 is going to be equal to 0.90 times 20,000 fully fresh air, which is equal to 18,000. Oops. But you didn't need to actually do any of that, because it's sufficient to say that this gets to 20,000 times 0.9, which for 1 minus e to the minus 600 over 20,000 t to equal to 0.9, that means e to the minus 600 over 20,000 t is going to be equal to 0.1, which means that minus 600 over 20,000 t 90 now, let's go ahead and put the subscript just to label this specifically, is going to be equal to ln of 0.1. You could say that's negative log 10 if you prefer. The answer is T90 equals 20,000. Well, it's going to be a negative 20,000 over 600 times ln of 0.1. This quantity is negative, and this quantity is negative. We know that T90 will be greater than 0. It only makes sense. This is just a quick check to make sure that we are on the right page. We haven't made some horrendous blunder. Do I need to simplify the numbers? I don't sense a strong need to do that, but obviously both of those are quantities you can type into your calculator. I'll call it done.